Good morning to all. Today we discuss the fifth problem in the design of spur gear. Design a pair of spur gear to have the following specification. Power transmitted N equal to 10 kW, N1 equal to 1000 rpm, N2 equal to 200 rpm. Material of the pinion is chromium nickel steel. Material of the gear is cast steel. Number of teeth selected on the pinion should not be less than the theoretical minimum. That is, minimum number of teeth on pinion to avoid the interference. First, we write down the given data. Power transmitted N equal to 10 kW, N1 equal to 1000 rpm, N2 equal to 200 rpm. Pinion material is chromium nickel steel. Gear material is cast steel. He asked designing complete spur gear. Now refer the table 23.6. The minimum number of teeth to avoid the interference for different gear system is given here. Now we assume the gear system is alpha equal to 20 FDI. For corresponding, the minimum number of teeth is 17. Now we select the number of teeth for the pinion is either you select 17 or 18 or 19. Whenever this condition is given, the teeth must be selected but not the assumptions. From table 23.18, for pinion material chromium nickel steel, allowable static stress is in the range of 448 to 517 MPa. For gear material cast steel, allowable static stress is 138 MPa. The remaining problem is similar to the problem number 1. Now we discuss the problem based on the given data. If number of teeth is given or the minimum number of teeth to avoid interference is given, then first step is to identify the weaker member. Second step is design. A bit is tangential tooth load. In this, the tangential tooth load is in terms of moduli. That is the first equation. B bit is tangential tooth load from the last equation. Here the dash means having some magnitude. The Ft value in terms of moduli and velocity factor, that is the equation number 2. After equating the equation number 1 and 2, we get equation number 3 in terms of moduli and velocity factor having some value. By trial and error method, find the standard moduli M. If instead of number of teeth, if pitch line velocity Vm or pitch circle diameter of pinion and gear or center distance is given, first we assume the number of teeth on the pinion. This number of teeth, this assumption is based on minimum number. For example, if alpha equal to 14.5 FDI is given, then you select or assume Z1 equal to 35 teeth. If 20 degree FDI is given, then assume 20 teeth. This assumption is only to find out the weaker member. Then move to the step 1 to identify the weaker member. Step 2, design. A bit, tangential tooth load. In this case, you get tangential tooth load is complete magnitude. That is the equation number 1. B bit, tangential tooth load from the Lewis equation. Here Ft in terms of moduli, that is the equation number 2. Now equate the equation number 1 and 2, we get this type of the equation. By trial and error method, find the standard moduli M. Next, we move to the another problem. Design a spur gear drive to transmit 12 kW from 1500 rpm. Motor to a compressor runs at 50 rpm. First, write down the given data. Power transmitted is 12 kW. N1 is 1500 rpm, N2 is 50 rpm. Here, first we calculate the velocity ratio. As the velocity ratio is more than the 10, multi-stage reduction is recommended. Factorizing 30 into 5 into 6, a two-stage reduction drive can be used. This is the two-stage reduction drive. Select smaller speed pair for the gear design. This is the smaller speed pair. For that, speed of the pinion is N1 equal to 300, N2 equal to 50 rpm. Velocity ratio is 6. Assume alpha equal to 20 degree FDI and Z1 equal to 18. Pinion material is cast steel 0.2% carbon heat treated. For that, allowed statistics is 173 MPa. Here, driven mechanism is compressor. For that, CS equal to 1.75. Now, the problem is similar to the problem number 1. Now we take some note. If number of teeth are not given and pitch circle, pitch line velocity or pitch circle diameter and center distance also not given, then select minimum number of teeth to avoid the interference for the given gear system. Second, if material of the pinion and gear is not given, then select any kind of material for pinion and gear, but generally select chromium nickel steel for both pinion and gear. From table 23.18, allowed statistics for that material is given, or select cast steel 0.2% carbon heat treated for pinion. From table 23.18, allowable statistics for that material is 173 MPa. Generally, select chromium nickel steel for pinion. After equating sigma naught 1 y1 equal to sigma naught 2 y2, calculate sigma naught 2 value and select material from the table 23.18 must be nearer to sigma naught 2 value. Third one, if pressure angle is not given, generally assume alpha equal to 20 degree FDI. Fourth one, if class of gear is not given, generally assume class 2 carefully cut teeth. If class of gear is known, then error F is obtained from figure 23.34a. Otherwise, based on velocity Vm, the error F is obtained from the figure 23.35a. Fifth one, if type of load and type of service is not given, generally assume medium shock 8 to 10 hours duty per day. From table 23.13, service factor is 1.5. If for the driven mechanism compressor load is given, then select CS equal to 1.75. For the driven mechanism turbine blower is given, then service factor is you take 1.25. For the driven mechanism pump is given, for the corresponding service factor you take 1.5. If material name is not listed in the table 23.18, we must know the equivalent material name. For example, bronze spur gear is equivalent to the cast iron gear. C45 steel untreated is equivalent to the steel SAE 1045 untreated. Seventh one, instead of allowable bending or steady stress, if yield stress or ultimate stress is given in the problem, then calculate allowable steady stress from this equation. If factor of safety is not given, then assume factor of safety equal to 2. If factor of safety is asked, then calculate effective force from this equation. Then calculate beam strength of the vehicle from this equation. In order to avoid the breakage of the gear tooth due to the bending, the beam strength should be more than the effective force between the machine teeth. That is, FB is greater than the F effective. Therefore, factor of safety equal to beam strength is divided by effective force.